So we did cover some concepts related to rotational motion. The ideas of rotational motion are new, different. That's why you may think that is a bit more complicated than the linear motion. But in fact, the problems related to the rotational motion, they turn out to be easier than the linear motion. It's mostly the formulas, and you plug in the number, but obviously you have to pick the right formula. It would be your job. We also went over a quantity angular momentum. Does anyone remember what that was? If the object is rotating, there will be angle change involved and there would be momentum related to its rotation. That is called the angular momentum. Angular momentum also depends on the moment of inertia, like the rotational kinetic energy, and it also depends on omega. Now, would that always be constant? Just like if I apply change on both sides, so I can't remember that if I went over this or not, but I'm going to go over the conservation of momentum again in any case. Now moment of inertia should remain constant. If it is changing, yes, we have to apply the change with respect to time on both, but as long as moment of inertia is constant, we can apply the change of time only with the angular velocity. Now delta what is this? Angular acceleration? Correct? Do we all agree? Delta L over delta T. It's one of those, because when the velocity, angular velocity changes, there would be angular acceleration, which is, for rotational motion, it is called I alpha. Do you remember this I alpha equal to what? Newton's second law equivalent for rotational motion says that if there is acceleration produced and that is, if you multiply it by the moment of inertia, that gives you the sum of the torque, net torque acting. Okay? So that means the torque, net torque is equal to delta L over delta T. If there is no net torque acting on the system, if this is zero, if the system, there is no external force acting on it, then delta L over delta T would be equal to 0. Or you can say L is equal to constant. Right? Or we can also write it as or Li initially is equal to final angular momentum. Angular momentum, if there is no external force acting on the system may comprise on one object or multiple objects. If there is no external force acting on the system, and then that puts the torque equal to 0, or all the torques have balanced out, the net torque is 0, the angular momentum of the system would always be conserved. This is called the law of conservation of momentum. Or I can also write it as I initial final okay. This is very similar to the linear momentum. If you remember, in linear momentum we always said that if there are two objects, whatever it was initially, if two objects collide with each other and initially they both were at rest, they're going to move in opposite direction to conserve the momentum, right? You fire the bullet and gun both move in opposite direction to conserve the momentum. Rocket is fired, rocket moves forward, gases move downward, they conserve the momentum. That is the linear momentum. This is the case when there is a rotational momentum. And it is exactly the same. Just treat it as initial moment of inertia, initial angular velocity, final moment of inertia, final angular velocity. They will change accordingly. Okay? If you have, let's say, a satellite going in an orbit around the Earth, when it gets closer, and it has a elliptic orbit, not circular. The points where it gets closer, where the radius is smaller, when it gets closer, it starts moving faster to increase the momentum, increase the angular velocity. Where it is away from the Earth, there it's going to go slower because the radius is greater and it's trying to reduce the moment of inertia. And remember this moment of inertia that depends on the distance. When the distance is greater, moment of inertia would be smaller. Yes. You tell me. Yeah. That would make the object slows down because moment of inertia greater. So when I is greater, if I is greater, omega should decrease. When I is lower, omega should increase. Why are they doing it? In order to conserve the angular momentum. I have a platform here, which I'm always scared of stepping on. Sometime I did take the student services, but today I'm going to do it myself. So it can rotate. Initially, I'm going to set it up. So if which situation I'm going to have more inertia, like that or like this? Like this or this? This, right? Because now the more mass is spread, the inertia should be greater. Here, the inertia should be smaller. When they are closer to my body, that means my inertia would be smaller. Distance is smaller, inertia is smaller. So what should actually happen once I set myself into rotation? The result would be if I bring my hands closer, my inertia is smaller, I should speed up. I should rotate faster. As I move the hands away, I should go slower. I should go slower, right? Let's see if that is the case. I hope you notice the difference. Oops. Did you notice it? Is it clear? Clearly different or no? No? Oh my God. Caroline is not satisfied. I think if I have the dumbbell in the hand, so dumbbells are going to put more inertia to me, right? So I guess that is the way, or maybe I'm too scared of moving and falling in front of the class. I hope nobody makes a movie if I fall. For me, it's different. I can feel the difference. And if I do it faster, it's more noticeable. Anyways. Okay? So always the momentum in any situation, the momentum must be conserved. So when we see sudden rotation in the object, you are holding rotating bicycle wheel, and suddenly you change its direction. Either you are going to start rotating in opposite direction to conserve the angular momentum. So if there is something counterclockwise, if one side is counterclockwise, the opposite side would start going to the clockwise direction in order to conserve it. Are we good? Questions? Yes?
Okay, so when your hands are out, it was slower because your inertia was greater. Is that right?
Yes. So this is what you are looking at. When we say forces, external forces are zero. In fact, they are small compared to the internal forces that we don't really consider them. If there are no external forces, okay, which are disturbing the system, initial angular momentum should be equal to final angular momentum. Okay, so when inertia would be, so when my hands were out, inertia was greater. This needed to go smaller. Correct? When my hands were closer, this was smaller. Omega needed to go greater. So that one smaller and greater value at the end, products should be the same. All right? This is the same thing that we discussed when we said bullet should go faster, boat should move, the gun should move slower. Right? When the atom emits the electron go faster, atom recoils slowly. Those who study chemistry, they know that the atoms are emitting the electron. When they do emit the electron going to go faster because it's very light particle. But in order to conserve momentum, the atom would recoil as well, but that recoil is very small compared to the electron. Right? It's the same thing, very similar behavior, but in terms of rotation. Let's see how you're going to see. Angular momentum question could be very tricky. In a way, there would be some collision involved, initial and final. You know, two objects are maybe a bicycle wheel rotating. You stick another mass to the edge of the wheel, and that would slow down. What is the final momentum? What's the final angular velocity? What's the inertia? So there would be something which will happen in that problem, some sort of collision, and objects will lose some energy. They might stick together or they might separate out, but the total angular momentum should be the same. Now, like this problem, you have two disks. There are two disks rotating around a shaft, and this one, the lower disk, is rotating counterclockwise. It has a radius of 3.5 centimeter. It has a mass of 440 grams, and it is frictionless shaft, and it is moving with the speed of 180 revolutions per minute. Okay, this is the information given about the lower disk. There is a top disk too. I think it's a smaller radius. 2.3 radius centimeter, and its mass is 270 grams. And initially, so this one is omega I, this one is omega I 0. It is at rest. It's not moving, but the bottom one is moving. All right? It's not moving. So it's like maybe if this does not make sense, the picture, you may think that it's moving just by itself until you put another one. You hold it at the top, it's not moving, and then you just drop it on the other one, and then they move together. So you drop this is dropped on this bigger disk, and now they are combined as one disk. And now they are rotating together counterclockwise. Question is, what is the final angular velocity? Let me call one of them as A disk and B disk so that I can have a different symbol for it, something in subscript for each one of them. Is question clear? There is one disk, the other disk is at rest, okay, it's not moving with it, okay, and we know the radius and the mass for that disk is dropped on this first moving disk, and then they move together. Are they going to move slower now? Yes. Why? Because they are heavier now. What kind of collision is that? Inelastic kind of collision, right? They are sticking together. They would have lost energy in order to be together. Anyways, when they are together, now they are moving. We want to know what's the final velocity. What can we say? For this problem, with your eyes closed, you can say this is an angular momentum conservation problem, because something happened initially and then after, before and after. So when there is a before and after situation, like a collision, some sort of interaction between two objects, it's most of the time angular momentum conservation problem that you could use. So if the momentum is conserved, that means initially momentum, let me put them separately. I A omega I plus I B omega I, that should be equal to IA plus IB and omega F. Is that equation correct? I can use initially for A, initially for B. Is that equation correct? What does it mean?
It means that the result of the added inertia and angular velocity should be the same when the masses are added together and multiplied.
Correct. So whatever was the angular momentum of the first disk, angular momentum of the second disk, sum of both should be equal to the total angular momentum. Why did I put them together with the same velocity? Because once they are one mass, their inertia add up and they both will rotate with the same angular velocity. Okay? They will not have a different speed. Now what should I do? Very good. This one 0. Good. Is there anything else I can do? Or I should do? Do we know what is I?
Yes, remember I equals to the large square.
For a disk?
No, you had
Yes, you have to look at that table. That is for the disk. I can tell you, it's half m r square, where m is the mass, r is the radius. Okay, so we can use that formula with confidence in order to write the moment of inertia. Half mass of the first disk, radius of the first disk square, its velocity, half ma ra square plus half mb rb square, and then omega f. Is everything in the equation known except the omega f? Yes. Can we solve for it? Yes. You just plug in all the numbers. Make sure you convert the centimeter into meters and grams into kilograms. But conversion should not affect the answer. They will cancel out from both sides. So we are using revolution per minute. So if you are using 180, your answer will also be in revolutions per minute. So I got for revolutions per minute, the number I have here is 12.3 RPM. Yes. RA is 3.5. That's disk A. So its radius is RA. That's 3.5 centimeter. These are not meters.
Okay.
These are centimeters. Convert them to meter. This is also in centimeter. Okay. So did you put that in kilogram? Yeah, now you should put that in meters. You got that?
I'm working on it.
Somewhere close? 11.3? It's close to that. So it's better that we can check it with someone else too. Did you get?
You convert that to kilograms.
Even if you don't convert anything, I believe it should not affect your answer because it's the same thing on both sides, right? They cancel out.
Even this one.
Yeah, like grams are on both sides. Distance is on both sides.
Can I cancel these out or do I?
Halves? Yeah.
Yeah. Okay.
Half will cancel out.
Okay.
Kayla, did you get the answer?
No.
Not the same? Oh. If nobody gets it, then I have to do it. Samantha? Oh, yeah. 142?
I did. I don't know what I did. I did the conversions.
Mm-hmm.
This is 0.35 meters, 0.23 meters, 0.440 kilograms, 0.279 kilograms.
Mm-hmm.
And then you do arc radius squared.
Let me check then, okay? It's possible though, because it's 180, so going down to 12.3 is just such a big difference. Did you square root it? Omega at the end, because you will get whatever you get is going to be in as omega. Oh, just a second. Oh, no, that's fine. That's fine. That's omega, just omega. So, point. It's 140. Is that right? Okay. This is what I did not round anything. This is what I got. You get something different? Well, I would say yes, I did round it. Yes. Yeah. I didn't keep everything on the calculator and to call the significant figure. Probably your answer is going to be more, if you were on the calculator all the time, using all the number, your answer would be more accurate than mine.
It was really close.
What is it?
142.
Okay. 143?
142.3.
This one is more accurate then. Okay, if you don't get off the calculator, yes, I did get off the calculator. I did round it off on my way. And if there is a requirement to convert to radians per second, do you think you can do it? How many radians in one revolution? 2 what? 2 pi. Right? You will multiply it by 2 pi and divide it by 60. Good. Should we move on? All right. That's about it for today. So in our next lecture, and be prepared for a very short quiz, which we may have in the class, in next class or the class after that. I'm going to run a very short review for the final exam. Go over the dates of the final exam, what to expect, what not to expect for the final exam. Any questions that you have for me. So in next 2 classes, I'm up for that. You can bring the question. If you could tell me ahead of time, that would be great. I would know what I should know. So if there is any question that homework problem, everybody is having problem with, it's good for me to cover it in class. But that would take most of the class time. Okay, but I would know that I would use that class time for solving that problem. So if you could tell me ahead of time. So next 2 classes, we are finished with most of what we were supposed to do. Okay, now it's going to be mostly revisions, quizzes, and reviews. Okay, for the homework problems. All right, I'll see you on Friday.